So we are in S domain and we are examining the general analysis techniques in circuit analysis in S domain, and we are in here examining the general analysis techniques. We have already seen these classical methods. In this method we are going to use two any equations, two any unknowns. Any is the number of elements in a circuit, and then we said we are using many number of equations. Many equations means two any equations used in this classical method. There are alternative methods, node voltage and mesh current methods. We use less number of equations, and we have seen the node voltage method already. In this video we will be examining this mesh current method. Why it is general analysis techniques? Because by using these techniques we are finding out all the elements current and voltages, not just one of them. If you need to calculate one of the element current and voltage only, then the special analysis technique, which includes Thevenin Norton equivalent circuits in it, will be examined later on. So let's move to this mesh current method on the open board now. Then we've got to come to open board, and open board. Here, this circuit is the same circuit we use in the analysis of the node voltage method, and we will be using the same circuit in mesh current method as well. Why is that? Because you can check out this elements calculation in node voltage method and the mesh current method are going to be the same as now. So you can check this. So in this, now we've got to transfer the time domain circuit, which is this circuit here, this circuit, to the S domain. We have done it in node voltage method. I'm not going to repeat it in details here, but I can outline it by just saying we transfer these element impedances into S domain. So impedance of the inductor is 0.1 S. Impedance of the capacitor is 10 to the power 4 over S. So, and then independent voltage source voltage transfer from time domain to the S domain, which is this. So the first thing that we've got to decide is in this method what we are going to Kirchhoff, which equations that we are going to use in this method. So the name of the method is mesh current method. Mesh current method. When it is mesh current method, it is easy to make a decision right now, because for the meshes we are going to write Kirchhoff voltage law equations. So Kirchhoff KVL equations that we are going to write. So that is the first thing to decide. So we've got three meshes here. So we are going to write Kirchhoff voltage law equation for these meshes. The first mesh is this one, isn't it? So according to passive sign convention, this independent voltage source current is downwards. So this is IS. Since the IS is coming out of the node 1, since the IS current direction is the opposite direction of the loop direction, it's going to be minus IS. Oh, I made a mistake. We are not writing current equation, so that's a good mistake that I have done. It's good for you. You are writing Kirchhoff voltage law equation. This is current. You cannot write that. So you're going to clear this, and then we are going to write the voltage of this element. How I am going to, the sign of this voltage is going to be negative because these directions are the opposite, so minus. This voltage is Vs, independent voltage source voltage. So we know this Vs is equal to this, so you can replace this with this if you like. 10 to the power 4. So the second element in this loop, or in this mesh, let's say, is this resistor, 10 ohm resistor. So we're going to write this 10 ohm resistor voltage here. The sign is going to be positive because the direction here and the mesh direction are the same. So plus V10. I am not writing V10 here because I would like to write the final mesh equations without following the steps, because we have followed all these steps in time domain resistive circuits and in frequency domain. Now in here I would like to write the resulting equation directly. How I am writing it is easy. The voltage of this resistor is equal this resistor impedance multiplied with the current of this element. So resistor is this, and this element multiplied with this element current, let's say this is I10. So I wrote this I10 a bit upwards here. The reason is this: since we are using the mesh current method, we know that all the elements' currents can be written in terms of mesh currents. How I am going to write it? The rule is this: this element current is equal summation of the mesh currents which pass through this element. Example, this element, there is only one mesh current passing through this element. This is IC1. For this element, there are two mesh current passing through. One of them is one IC1, the other one is IC2. So come back to rule again. An element current is equal summation of the related mesh currents. The sign of these mesh currents must be chosen as positive if the element current and mesh current directions are the same. If they are opposite, you've got to put a minus sign in front of this mesh current. So by using this rule now, I can say that this 10 ohm resistor multiplied I10, if I looked at I10, there is only one mesh current passing through this element, and this mesh current direction is the same of this element current reference. So it's going to be equal IC1. IC1. What is this altogether? So this is equal to this one. Altogether this is V10, because I am writing Kirchhoff voltage law equation. The last element, it's the third element in this mesh, is this 20 ohm resistor. So similarly, the sign is going to be positive because this element current and the mesh current is the same, plus the voltage of this element equal 20 times IC1 minus IC2. How I wrote that? Summation of those two mesh current. Why is that? Because these two mesh current passing through this element. For example, this mesh current is not passing through this 20 ohm resistor, so it is not included in here. So how I made the decision about the sign of those mesh currents: if mesh current direction and this element current direction are the same, this sign is positive. If they are opposite, for example, this mesh current direction and this element current direction is opposite to each other, therefore it is minus. So I wrote here for the first mesh 3 terms here, and I've got 3 elements in here, so they are equal to 0. So the second mesh equation, KVL once again, KVL equations I am going to write for the mesh 2. So this resistor voltage is also seen in this second mesh as well. So it's going to be direction, the sign of this voltage is going to be minus, so minus of this voltage is net. That is 20 ohm resistor voltage. In this case, in this mesh, it's going to be minus 20 IC1 minus IC2. So the voltage of this inductor now. So I'm going to write, so the sign first. Sign of the voltage of this inductor is going to be positive because the mesh direction and this element current directions are the same. So plus. And if I write multiply times this element current gives you the voltage. So the impedance 0.1s multiplied the current of this element. In terms of mesh current, it is equal to IC2. Why is that? Directions are the same and there is only one mesh current passing through this element. So IC2. That is the voltage of the inductor. Now let's come to the third element here, which is a dependent source. So as I advised you already in the node voltage method, when you come a dependent source, wait a minute. The first thing to do is write the definition relation of this element. How you're going to write the definition of this element? By looking at the shape, you're going to say this is a dependent source. Since the voltage reference given inside the diamond shape, it is a dependent voltage source, of which voltage depends on a current that I, which is another element current here, this resistor current. So this I10 and this I is the same. So definition of this element, definition relation of this element is voltage current controlled voltage source voltage is equal 5E. So that 5E here is not the impedance, it is part of the definition relation. So if you look at this definition relation now, you could see only the voltage of this element in that definition relation. You cannot see the current of this element in this definition relation. So the current depends on the circuit it is connected. So it is going to be like that. It is not known, that means. So if you compare this definition relation with a resistor definition relation, you see the difference. In the definition relation of the resistor, that is VR, R times IR. In this definition relation, resistor voltage and current seen in the definition relation. But in this definition relation, this current does not belong on this dependent source. It belongs on to another element current. So this element current and voltages together is not seen in the definition relation. So these two definition relations are different. So you've got to pay attention to those, this definition relations especially. Now let's come to our equation now. The last element is this element, and this element voltage, I've got to write this. Why is that? Because I am writing Kirchhoff voltage law equation. So summation of the elements within a mesh is equal to 0 is Kirchhoff voltage law equation. So the sign is going to be plus. Why is that? Because the current reference for this element, according to passive sign convention, is downwards. So this direction and this mesh directions are the same, so the sign is plus. Now what I am going to write here, I'm not going to write this VCCVS because my resulting equation is going to be mesh current equation. I could transfer this by using the definition relation of this element. I can transfer this term to mesh currents. So that means 5 times I. I is this current or this current. This current is equal to IC1. So that I current is this resistor current, and for this resistor there is only one mesh current, so that mesh current is equal to resistor current as well. So this is going to be now IC1. What is this? This is equal to this I here. What is altogether this is this voltage here. Make it different color. That voltage here is this. Okay. So what we wrote here, Kirchhoff voltage law equation, voltage of this element, this voltage of this element, this voltage of this element. So this is the second mesh equation is equal to 0. Make it blue again. So for the last mesh, that's the third mesh. So minus of this element voltage. Why it is minus? Because this direction is opposite to that direction. So minus 5 IC1. And the capacitor voltage is, first the sign is positive because this direction and this two direction. That means third mesh current direction and this element current same direction, it is going to be positive. Write the impedance 10 to the power 4 over S, that's the impedance, times the current of this element, which is equal IC3, because this is the only current, mesh current passing through this element, IC3. And the last one, this resistor voltage is, the sign is going to be positive because this red and this direction are the same, plus 50 times impedance times this element current, which is equal IC3. Look at now those three equations. The number of unknowns are IC1, IC2 and IC3, and we've got three equations, three unknowns, three equations and three unknowns. Then we can find all these unknowns. How you're going to find it, it seems easy. Why is that? If you look at this now, only the IC1 and IC2 included here. So you can find out IC1 in terms of IC2, replace it in here, you can find IC2, then IC1, then if you know the IC1, then you can calculate IC3 by using this last equation. So if you do so, you're going to end up with IC1, IC3, IC3 here. So that is the three unknowns that we have found. So if you found all these three unknowns, we are saying all the elements currents can be written in terms of the mesh currents. So you can find all the element currents. Here you are. 10 ohm resistor current, 20 ohm resistor current, inductor current, capacitor current, all found here. So if you know these element currents, by using the definition relation, you can find these element voltages. So you can find the, you can say that what about the dependent source? If you remember, the dependent source voltage, current controlled voltage source voltage was equal to 5I. So since I is IC1, since you know the IC1, then you can find that this. So you found the dependent source voltage What about the current of this element? So you can write all the elements current in terms of mesh currents I already said. So this is this element current in terms of mesh current. So you already found IC2 and IC3, then you can calculate this element current as well. So at the end, you found out all the elements current and voltages by using this method. So if you compare now last three methods that we use, the first one, the classical method, we wrote to any equations, to any unknowns. We had 7 elements included in our circuit. We used the same circuit for all these analyses. So it's going to be 14 equations you're going to write and solve these 14 equations. In the node voltage method, we wrote 5 equations and 5 unknowns. So in here now, mesh current method, we use only 3 equations. We did not need to write any supplementary equation in here, but in the node voltage method, we need to write 2 supplementary equations. So which one is good? Of course, you're going to say this one is good. So you might ask now, saying that if mesh current method is better than the node voltage method, so ignore the node voltage method, why do we need to know that method? The answer is we do need, because depend on the circuit, sometimes the number of node voltage method might be using less number of equations than the mesh current method equations. Therefore, you've got to know both of them. And then, if you are good enough, at the beginning, you can choose which method is better than the other one by looking at the circuit. By saying how many supplementary equations do you need for different methods. Once you get that, so you can make your decision which method that you're going to use. So this is one thing that I've got to raise on this subject. The other one is this: if you are using these methods, we already know that all the elements current and voltages depend on independent sources functions. So let me show it to you. Our independent source was Vs, and S domain correspondence function is 10s over s squared 10 to the power 4. So I am saying now this should be seeing all the elements currents and voltages. How? Here you are. So in here already done it. So if I multiply this by 10 and this by 10, nothing would change, isn't it? So if you look at this part now, that is Vs here. So if you look at this one, 10s, if you consider this one is 5 times 10, isn't it? So this again, so you might consider that, okay, that is Vs. If you write this s squared, s times s, and multiply 10, and this, that was 30, make it 300. So now this once again is Vs. You see all the mesh currents depends on that Vs. Similarly, you can say that all these currents and voltages, all elements current and voltages depends on that. You could easily see that by saying this, isn't it? This is a linear algebraic equation, isn't it? So B includes that independent source. B includes that Vs here. So if you say that that's mesh currents, IC 1, 2, 2, mesh currents is inverse of A matrix multiplied B. So that means all the mesh current depends on that Vs included that B matrix. So mathematically it is easy to see that. So what you could do in order to make your calculations a bit simpler, you can keep that Vs as it is until you get all the unknowns. At the end, you might write that Vs at the end, finding all the elements, current and voltages. So that is the end of this video, then let's stop here.